So he's going to talk about how they're going to rescue Hubble constant using standard candles and Sirens. So let's welcome him.
Okay, so thank you. So today I'm going to talk about this work which we submitted just on Monday. And yeah, let's see how we can rescue H0 and why it needs to be rescued. So I think that I already gave a pretty nice introduction to what we are trying to do in cosmology. So I'll just make a brief comment that in cosmology we have this so-called standard model where we assume that the universe is homogeneous and isotropic on sufficiently large scales, and we assume that GR is the theory of gravity that is valid for the whole evolution, and then we try and predict how the scale factor evolves as a function of time. So the scale factor is like the essentially a factor that determines the distance between any 2 points. So the key ingredients when we put all this together, we also need to put in some values that we determine from measurements. So this is same as for, let's say, in the standard model of particle physics, we need to put in the charge of the electron or the mass of the Higgs boson to make any quantitative predictions. So the same goes for cosmology. And in particular for this scale factor, what we need to put in is the baryonic matter density, the dark matter density, the dark energy density, and the Hubble constant. So the Hubble constant is just the current age of our universe, or it's proportional to the current age of our universe. So today I'm going to just talk about this one parameter. So naively we would expect that this number should be constant because after all it is the age of our universe, and it should not depend on which experiment or which probe we use to make a measurement. However, current observations paint a different picture. So on this plot I show, taken from this paper, I show the results of 10 different measurements of this same parameter, the Hubble constant. And these 10 measurements have been divided into two sections. So on the top we have the early universe predictions for the Hubble constant. So these are from the Planck satellite, which measured the cosmic microwave background, and that gets a value of like 67. And similarly, we have this result, which comes from galaxy clustering or lensing, combined with Big Bang nucleosynthesis measurements. And these both are consistent with each other and give a value of roughly 67. And in the bottom part here, we have the so-called late universe measurements. So these are measurements made much closer by to us. So for instance, this is from type 1a supernovae out to redshift 1.4. This is from tip of red giant branch stars. This is from strong lensing, and there are all others. So these are all measurements of this same value from closer by probes. And we see that they are all, again, consistent with each other. But the problem is that they are all inconsistent, at least at 4 sigma level, with the predictions from the early universe. So this is kind of surprising, right? I mean, this should be one number, whatever experiment we use to probe it. So there are two possibilities. Either this arises from some new physics, in which case this is very exciting because it gives us something to do, or it is coming from some systematic errors between these two sets of measurement, in which case maybe it's not that exciting. But anyway, to determine which one it is, we need to at least rule out one of these two possibilities. So what I am going to show here is how we can rule out this second possibility, which is that this discrepancy is coming from systematic errors. And the way to do that is kind of simple. You can just go and measure H0 with some different probes, and those probes will suffer from different systematic errors, and then you would know whether this discrepancy arises from systematic errors or not. So how do we go about measuring H0? Well, one possibility is to measure distances. So I show here a plot of the luminosity distance as a function of redshift And these different lines show different cosmological models. So omega lambda is the amount of dark matter, dark energy density in the universe, essentially. And omega matter is the amount of matter density in the universe. So what we see is that at least at the very low redshifts, for all these different models, the luminosity distance is linearly dependent on redshift, and it has a constant slope. So it turns out that it behaves like this, and thus by measuring the luminosity distance at low redshift and this slope, we can get a value for h0. We can also measure luminosity distances out to higher redshifts, and then we do need to assume something about all these other parameters to see which line is the correct description of our universe. So then the question is, how do you measure luminosity distances? And this is where standard candles or standard sirens come into play. So standard candles are essentially type 1a supernovae. This is because they have a more or less fixed intrinsic brightness. What that means is that, let's say in this plot here, I show the absolute magnitude of a supernova as a function of time. So we see that it rises to some maximum value and then decays. And the spread of this maximum value is quite small. And so the fact that it peaks to roughly the same magnitude is nice. But also we can even reduce this spread by noting that the peak magnitude is strongly correlated with how it decays. So when you correct for these effects, we find that type 1a supernovae have a fixed peak brightness. Then if all the supernovae have a fixed peak brightness, and we can also observe their apparent flux, then by this simple relation between the emitted brightness and the apparent brightness, we can determine their luminosity distance. We can also separately measure the redshift, and then this gives us the luminosity distance as a function of redshift. So moving to standard sirens. So standard sirens are gravitational wave sources. One example of these sources is these binary neutron star systems. So you have a couple of neutron stars, they spiral into each other, and in that process they emit these gravitational waves. Because these are neutron stars, they also emit electromagnetic waves, and we can use that to get the redshift. And the gravitational waves we can use to get the luminosity distance. So the idea is that the waveform of the observed waves gives us some information about the emission amplitude of these gravitational waves. And then we know that the amplitude of gravitational waves decays with inversely as the distance from the source. So then by using the observed amplitude and the emitted amplitude, we can get the luminosity distance. And combine that with the information from the electromagnetic radiation, we once again can determine the luminosity distance as a function of redshift. And this whole process, because we use the frequency of the emitted waves to get some information about the intrinsic properties, is why they are called standard sirens. So for type 1a supernovae, actually what we measure directly observationally is not the luminosity distance itself, but this quantity called the distance modulus. And that is just related to the luminosity distance via this relation. Delta n is some scattered in the distance modulus. So as you can see in this plot, this is the distance modulus as a function of redshift for many different supernovae. And the solid line here denotes the prediction from assuming a homogeneous and isotropic universe. However, as you can see, there's a lot of scatter around this solid line, and not all these points lie on this line. So this happens because the universe is not exactly homogeneous and isotropic, because we see structure around us. And so this scatter is actually caused by mainly three different physical effects. So one is lensing, one is peculiar motion, and the last one is intrinsic uncertainties. So the intrinsic uncertainties includes all uncertainties that come from getting the peak brightness correct or from any measurement uncertainties. So this does not contain any cosmological information. However, lensing and peculiar motion both have cosmological information. So let's look at these in more detail. So lensing is caused by light passing through matter along the line of sight and gets bent by that matter. So for instance, here a massive galaxy in the line of sight to a source galaxy gets bent because of gravitational lensing. And the farther away a galaxy is, the more matter light has to pass through more matter along the line of sight, and this gets more bent or more lensed. So lensing effect is most prominent for higher redshift sources. And in terms of brightness, we can understand this by imagining that lensing would probably make this galaxy appear brighter, let's say, and thus it would appear to be closer than it actually is. So we can actually model this scatter due to lensing and get something like this. So the important thing is that there is cosmological information about h0 and omega n, which is the matter density in the universe here. And there is also cosmological information in this power spectrum, which is just roughly the amount of matter present along this line of sight. So this is in fact also sensitive to very fundamental physics, such as the mass of neutrinos or the dark energy equation of state. Now coming to peculiar motion. So peculiar motion just changes the observed redshift of a source. So if you have something that is moving towards you, it gets blue shifted. If you have something that is moving away, that appears red shifted. And because the luminosity distance is an increasing function of redshift, this makes objects appear closer to us or farther to us, depending on whether they are blue shifting or red shifting. So the overall scatter can once again be modeled, and here the cosmological information is not only contained in this free factor and this power spectrum, but there's also this Newton here, which essentially is the rate at which structure grows in the universe. And this is also very sensitive to neutrino mass, for instance. And moreover, this effect is only important when the peculiar velocities are of the order of the Hubble velocity, because that's the only regime in which the change in redshift will be significant enough. So therefore, these effects are only important at low redshift. So this plot here now confirms sort of our intuition about the importance of these relative effects. So this is a plot of the scatter as a function of redshift. So as we saw before, lensing becomes more important at higher redshifts. Peculiar velocities have a smaller contribution as the increased redshift, and the intrinsic scatter is just a constant across redshifts. So by putting all this together, we can finally start to get some constraints on our cosmological parameters, which is what I show in this plot. So here we have 5 cosmological parameters that are of interest to us. So mu is the sum of neutrino masses. So this is as yet still undetermined quantity. Particle physics just gives us a lower bound at 0.06. So we need cosmology to give some more constraint on this parameter. W0 is the time-independent part of the equation of state of dark energy. So for a lambda CDM model, for instance, W0 is -1. This again does not change with time. WA is the time-dependent part of the equation of state. So for a lambda CDM model, it is just 0, which means that the equation of state remains constant with time. Then we have omega CDM, which is the cold dark matter density in the universe. And then finally, we have the Hubble parameter H, which is the same as H0, except for a factor of 100. So, and in red here, I consider supernovae at very high redshift, so that's redshift 0.2 to 1.8 roughly. And in blue, I consider combining these high redshift supernovae with information from low redshift gravitational waves. So for the high redshift ones, we only consider lensing because peculiar velocities are not important. And for the gravitational waves at low redshifts, we only consider peculiar motion, since again lensing is not important at low redshifts. So the most striking thing to note is how much these contours shrink when we add low redshift gravitational wave information. So for instance, the neutrino masses get reduced by a factor of almost 3 just by adding low redshift gravitational wave information. So the reason that this happens is because by measuring the luminosity distance of gravitational waves, which we can measure very precisely, we have an almost perfect measurement of the Hubble constant, and that is also seen in this plot, where you can see that we have almost a perfect measurement of H. So now with this perfect measurement, can we actually say something about the Hubble tension? And turns out yes. So in this plot, I show the constraints obtained in the Hubble constant and dark matter density plane. And I marginalized over all the other parameters, so neutrino mass and dark energy equation of state. And the blue contours show results from combining gravitational waves with low redshift supernovae, which we do to maximize the information in this redshift. And then the red contours show the constraints obtained when we just use high redshift supernovae. So what we see is that the error bars are small enough that if we get a simultaneous measurement of the Hubble constant in these two redshift regimes, we can be sure that it is originating from systematic errors and not from any new physics. Therefore, to conclude, I think that we can resolve the Hubble tension once we can combine different probes. Different probes would suffer from different systematics, so this will rule out systematics as a cause of the Hubble tension. And by combining standard candles and sirens, we have shown that you can rule out new physics as the cause at more than forcing. Thank you.
Okay, questions? Comments?
Sad. On the forecast, you say you use the high redshift supernovae.
Mm-hmm.
And is that the prediction, or is that actually based on real observation of data?
No, this is a forecast for W first. So
And that's assumed long cosmology.
yes.
That's
I mean
what
that
you-
we can choose on our own what
That's right. Yeah,
fiducial
it's
cosmology.
all-
Yes.
So I have a somewhat ignorant question, more general comment. So why is it so important to measure functionality to whatever precision?
I-
First slide is like 66 to 80, right? It's
Yeah.
like the same number.
So I think in general it's not that necessary, but now with this tension, I think it has become more important to clarify what is happening. So that is why people want to measure, because I mean, if it is 5 sigma discrepant, that really points to something, right?
But I guess I was thinking like, I mean, what difference does it make? Is it a difference between having life in the universe and not having life?
Well, I mean, we still have life, whatever the value of it turns out to be. But yeah, I mean, it's just a precise measurement, and also in principle, it is a measure of the energy density of the universe today. So in a sense, it tells you how much, like what's the actual value of the dark matter density. So not just fractions, but the actual numbers.
Okay.
Hubble constant is a function of position, not a function of time.
Okay, sorry, I said yeah.
I think your question is applied to also the importance of measuring speed of light to precise gravitational constant. This should be fundamental constant. It should be on the textbook for junior high school in the future. That's what I think.
Okay, any more?
So for simulated, I think the importance of measurement of Hubble constant is using as a parameter in the cosmological simulation, and simulate whether they can fit with the observation like a CMB or sigma A kind of.
I guess we don't need very high precision for that.
Yeah.
Okay, any more questions, comments? Okay, if not, then we can thank the speaker again.